My guest tonight is Carl Zimmer. Carl wrote this book, which was published last week. It's called Life's Edge, and it's called The Search for What It Means to Be Alive. Carl began writing about science for the New York Times in 2004, where he now writes his weekly column, Matter. He has won tons of awards for his work, including the Stephen Jay Gould Prize, awarded by the Society for the Study of Evolution. He's been the author of 14 books about science. His most recent, She Has Her Mother's Laugh, The Power, Perversions, and Potential of Heredity, was published in 2018. And I had the pleasure of interviewing Carl in person. So it was probably the last time I saw him in Manhattan in front of an audience. So that was kind of fun. Carl, you want to turn your camera on and say hello to everyone? And
hey, everybody. Thanks for having me, David.
Oh, you're welcome. Thanks for, it's nice not to be talking about COVID-19, but you did publish something last week in the New York Times about whether the COVID virus was alive. So since today is the first anniversary of the World Health Organization declaring this pandemic, I never think of viruses being living organisms, but I guess they are.
Well, it really depends on who you ask. After I wrote that piece for the Sunday Review in the New York Times, I got an email in the morning from a scientist who told me, of course, viruses are not alive. And you ask any expert and they'll tell you that viruses are not alive. And then that afternoon, I got another email from another expert who said, of course, viruses are alive. And you ask anybody and who knows about viruses and they'll tell you that they are alive. So, you know, they both can't be right. Or maybe they're both right in some way that's actually really deep and interesting. But you know, viruses are one of these things that really can vex us when we think we know what life is, which is the idea that I explore in the book of what do we mean by life? What does it mean to be alive, and how do we look around at the world and figure out what is alive and what isn't?
Well, you're right. There are many definitions of life as people trying to explain it. And you also give the example of a scientist who had a rabbit in the lab and say, well, if a single rabbit can't reproduce itself, so you could argue that it's not alive. Now, every rabbit I see seems very lively to me. So how is that definition even possible?
Well, you know, again, it comes down to what your definition of life is. And, you know, it's really kind of odd that that biologists come up with literally hundreds of definitions and keep publishing new ones. Mm-hmm. And they're not converging towards one agreed upon definition of life. It's a little bit akin to if, you know, astronomers couldn't agree on what a star is, or chemists were wildly divided on what molecules are. It's kind of an embarrassing situation, but it's also a revealing one because because it tells you something about the nature of life and what we have yet to figure out about it. So so a lot of definitions of life will pull in a few hallmarks. So reproduction is one of them. And so, you know, I write in the book about these different hallmarks. And so for the hallmark of reproduction, I just write about a maple tree and how a maple tree makes new maple trees. It's an amazing, remarkable process by which, you know, they produce pollen and then fertilize these ovules, and then you have the incredible rain of samaras and so on and so forth. Rabbits obviously have their way of reproducing, but that's rabbits plural. There's no rabbit that ever just sat around and spontaneously reproduced itself. So if you say that something has to be able to reproduce itself to be considered alive, you know, one rabbit on its own kind of is not really alive. Now, people could, reasonably take issue with that. This was the example that we're talking about came from a Nobel Prize winner named Albert Szent-Györgyi, a Hungarian biochemist,
Mhm.
who gave a big lecture about life in 1947. So, one could say to him, okay, wait a minute. When I say that something's alive if it can reproduce, I mean that it can potentially reproduce with another member of its species. Okay, fair enough. But that still doesn't really get us out of the trap, because there are species where that doesn't work. And one example I gave in the book is a kind of fish called the Amazon molly. And it's the result of this whole species came about when two other species interbred. And they produced this new species, which has a very odd way of reproducing. An Amazon molly will give birth to daughters, nothing but daughters. And these daughters are perfect clones of itself, because it just kicks its eggs into development, and then they just turn into basically clones of itself. But the catch is that Amazon mollies cannot actually reproduce by themselves. They have this weird sort of evolutionary vestige where these female Amazon mollies have to mate with one of their parental species. So they go and they find a male from one of these parental species of fish, and they mate with that male fish. The male's sperm actually enters the Amazon molly's eggs, but then the Amazon molly's eggs have enzymes that shred their sperm, so they have no contribution to the genes in their offspring. But they need to mate to have that trigger to get the ball rolling. So you can kind of consider them as sexual parasites.
Okay.
They have to have sex with another species. So this whole species now cannot reproduce on its own. It needs another species. So, every time that you may think that you have a definition that is really airtight, you will very often just run into more trouble, because you will exclude something that we sort of intuitively feel is alive. Obviously a rabbit's alive. Obviously this fish is alive. Or the flip side is that you may end up with a definition that's so loosey-goosey that, hey, a snowflake is alive or a hurricane's alive. And some people may want to say, yes, I believe that life is everywhere. But, I think most biologists would be like, nah, I don't study snowflakes. I want to stick with fish, bacteria, maybe viruses. So there's this constant struggle with definitions. And, some philosophers have argued, well, maybe the whole problem is that you think that you can find a definition when maybe you can't.
Okay, so NASA has a definition of life. Life is a self-sustaining chemical system capable of Darwinian evolution and consider the specific features of the one life we know. So I don't know if I said, okay, all right, okay. So what does that mean? So let me ask you. So when you wrote your last book, She Has Her Mother's Laugh, it was kind of kicked off because you were going to go to a genetic counselor for the birth of a child.
Mm-hmm.
And you said you had never really thought about heredity. So I guess I'll ask you this question. What kicked off the reason for this book? I mean, I know that you wrote an article in 2011 about slime. I found that article about slime possibly being, an answer to evolution. So, but what made you decide to write a book?
I'm finding that books that I'm writing these days, they have a long, slow fuse. Like they've been brewing in my head for quite a while. So that She Has Her Mother's Laugh about heredity, I just sort of realized that I was really deeply fascinated with heredity and what it is and how we misunderstand it very often. And I think it really did, the mysteries of heredity really did hit me when my daughter was on her way, and we went to this genetics counselor. My daughter is now in college, so these fuses can be long, and I think Life's Edge, I think lots of kids will ask their parents, what is life, and they probably don't get a very satisfying answer. I probably asked my parents that when I was a kid, and I probably sort of puzzled over it. And I was of the generation that eagerly awaited Viking, the space probe going to Mars, and just wondering what kind of life they might find. And they kind of sort of didn't really find anything, but didn't rule out the possibility there might be life there that they couldn't see. And it sort of left me wondering, like, well, what are we looking for exactly? And then I became a science writer and I started specializing in biology. And I would, hang out with scientists who would be studying dolphins or redwoods or jellyfish or what have you, talking to them for articles and so on. And we would have it would be really a revelatory experience to learn about those particular species. But, if you stepped back and asked them about, well, what does this tell us about life itself? What do you think life is? A lot of times they would not really feel comfortable to even answer the question, or they might give one of these unsatisfying answers. And, that has sort of gotten me intrigued about how you can have this profound question at the heart of biology, which keeps slipping away from resolution. And there are big stakes to this question. People are always arguing about when life begins. Like that's the heart of the abortion debate. Or when does life end? We have these disputes over brain death, for example. Mm-hmm. These are like intensely personal, legal, ethical questions. It's not something for, I'm sure there's lots of late night dorm conversations about this, but there are conversations about this in court. There are conversations about this, in political debates. And, you have NASA going back to Mars now with, probes that are much more impressive than Viking, with, Perseverance has a helicopter with it. I mean, it's so cool. But it's still going there partly to look for signs of life. And yet we're still not that clear on what it is we're looking for. We're kind of, we know, like, well, maybe if the life on Mars is like life on Earth and we could know what kind of fossils to look for and so on. Okay, but what if Mars had a different path to life? That's another big question. And what I began to appreciate as I explored this more for the book is that the situation we're in now is just part of a big, long, rich history of scientists struggling with this question,
as well as philosophers.
Yeah, absolutely. Yeah. And it's interesting because, in the 1600s, when a lot of these issues really began to emerge in the sense that we deal with them, there weren't scientists. They called themselves natural philosophers. I think it would be a good idea for the scientists to think about philosophy a little bit more when these issues come up, because for example, like the question, what is life? People will say, oh, you're talking about Ernst Schrödinger and his famous book. So Ernst Schrödinger, the 20th century physicist, wrote a book called What is Life? Incredibly influential, important book. However, there was a physician and chemist who said in, I believe it was 1708, George Stahl, his name was, said, what is life? I mean, this is the central question that we're trying to address. And so people have been wrestling with this issue for a long, long time. And it has led them into some spectacular failures. This is part of science that is This is not a story of easy success and triumph. This is a story of failure after failure after failure. And in a way, we still have yet to succeed. The science has not won this game yet. There may be a theory of life in the future, just like there's a germ theory of disease. There's a theory of chemistry to explain matter. We may have a theory of life before too long, but we don't have it now. And I don't know when we're going to get it. So, we're sort of in an age of alchemy when it comes to life, I think.
Okay. So I wrote down in bold letters, so explain vitalists and the debate over that. And Henri Bergson, who also became very popular, he wrote a book and lectured all over the world, I think. So why don't we talk about vitalists a little bit?
Yeah, sure. Well, this is part of the fascinating history of trying to make sense of life. If you start by looking in the 1600s during the scientific revolution, you have someone like Descartes, who is trying to recast much of life in terms of mechanics, thinking of thinking of living things as machines where they're just made of parts that respond to different forces, and you can ultimately explain the movements of animals and their behavior in terms of machinery in a metaphorical sense. But you have these, so-called mechanists or mechanical philosophers who really champion this, not just for animals, but for the human body. So you would have doctors who would say, we have to treat the human body like a machine, as if it were mechanical. Then there were people who really responded in a very antagonistic way to all of this. These anti-Cartesians, they were sometimes called, enemies of Descartes. And eventually, through the 18th century, they came to be known as vitalists. Each of these so-called vitalists had their own very sophisticated views about life. But if you kind of, use a broad brush to paint their portrait, basically the idea is that, yes, maybe you can use physics or basic chemistry to explain some things about life, but fundamentally, there's something profoundly different about living matter. And some people thought that it was, actually a different substance, or that maybe there was some sort of vital force that gave living things their organization, their purpose, all these things that it seemed like just simple physics couldn't explain. And this tension kept playing out even into the 19th century, where chemists started discovering, we can actually make a lot of these chemicals in people's bodies. We can make them from scratch. We don't need a body to make them. We can do it in our lab. And so this inspired all sorts of debate and angst, and so the vitalists would push back and say, fine, that may be true, but still that vital force remains central to life itself. This even lasted in the 20th century. And you mentioned Henri Bergson. The philosopher, he would talk about the élan vital, which is kind of a descendant of that vital force from earlier generations. People love to hear this. So he showed up in the early 1900s in New York to give lectures about this. And apparently, reportedly, this was right when cars were becoming common in New York City. And he reportedly created New York City's first traffic jam because so many people wanted to come hear him talk. And there was he had tea with the wives of the professors at Columbia, which, very clearly dates this experience. Apparently, like, thousands of people just went to just look at him having tea with the wives. So why was this so popular? Well, I think because people felt that that the biochemical or biophysical view of life could be a little disheartening. Like, is life just a matter of molecules in motion? What does that mean for our own personal lives? Where do we find meaning? And so it was more comfortable to sort of have a almost mystical view that there was some vital force that science would never be able to capture. And even today, when scientists are trying to explain life and they're in a debate and someone is trying to make a case for maybe a particularly abstract explanation for how life works, you'll still find scientists accusing them of being vitalists. So it's still an insult that hangs on. The vital force is gone, but vitalism remains, maybe because we're still struggling to explain life.
Okay, so for the audience, if you have questions, please put them in the Q&A box. We only have one question, so I'd like to see it fill up. So in this book, you said you visited NASA's Jet Propulsion Laboratory to build chemical gardens. You traipsed into an abandoned graphite mine with scientists studying hibernating bats. More courage than I would have, especially now. Fed rats to pythons. I did that once, as you learned about their extreme metabolism. And visited a lab where slime molds solved mathematical problems. So let's talk a little bit about slime molds, because you mentioned them, and then about, I think, liposomes. Yeah.
Right. So slime molds. I just for in case people don't know what slime molds are, they're very much worth getting to know. If you go out in the woods in the summer and you see some weird patch of strangely colored protoplasm on the forest floor, something that looks like maybe a dog threw up, that's your slime mold. Slime molds are distantly related to fungi and animals and plants. They're eukaryotes. But a slime mold that you see, it can be like as big as a dinner plate or a placemat. That's a single cell, but it grows in sort of tentacles that it reaches out in different directions to feed on bacteria that it encounters on the forest floor, on logs, and so on. I got really fascinated with slime molds while working on this book because I wanted to start the book sort of in the safe territory of life as we know it, things that we can agree are life. And while we can't define life definitely has hallmarks. And there's life evolves, life has metabolism, and life also is able to life has a certain kind of intelligence. It's able to, by which I mean, I don't mean like that it can, all living things can take an SAT test. What I mean is that living things are able to take in information from their environment and use that information to make a decision about doing something, so that they don't just behave purely at random. There's a bias to things that are going to benefit that living thing. And so here you have slime molds, which don't have a brain. It's just one giant cell full of protoplasm pulsing around. If you go to a lab where people study slime molds, and there are these labs, I went to the lab of Simon Garnier at the New Jersey Institute of Technology, and they'll put like a slime mold in a petri dish, and you give them a little oatmeal, a little cube of oatmeal, and over the course of hours, the slime mold will sniff out, taste the scent of the oatmeal, and find it and feed on it. Now you could put the oatmeal on the other side of a maze, and that slime mold will figure out how to get through the maze. You can give a slime mold two different kinds of food, one that has a lot of protein, one that has a lot of carbohydrates. The slime mold will reshape its network so that it is feeding in the optimal way on each one of them to get its perfect combination of nutrients, which is actually sort of a slime mold version of solving a very old mathematical problem. So, how is it that slime molds can do these calculations? How can they make decisions? Well, that's still kind of mysterious, honestly. But Garnier and his students are trying to understand how chemicals pulse around inside of the tentacles of the slime mold, and how it's able to turn what it encounters in its environment into these different kinds of pulsations that kind of interact with each other. It sounds freaky, but like that's the most compelling explanation for how these slime molds do what they do. So so in the book, I look at these, consider these different hallmarks, and I go and I looked for the coolest examples of them. And so for the kind of intelligence that life has, my favorite example is slime molds. And tell me, remind me again, I got so enchanted with slime molds, I forgot what the other thing you want to talk about was.
Liposomes?
Liposomes, yes, liposomes. So liposomes actually people may have been reading about liposomes recently because of these coronavirus vaccines.
Right.
So the Pfizer vaccine and the Moderna vaccine, they are a little fragment of RNA encased in a little sort of oily, fatty type membrane bubble. The material is that's made of is lipids. There are lipids in olive oil and in fat and so on. And they spontaneously form bubbles. And so these bubbles made of lipids are called liposomes. So liposomes are great as a way to deliver medicine because they don't really provoke a big immune response. They look totally harmless to the immune system. So the liposomes that we are using now, that people are getting vaccinated with, they exist because of some pioneering work that some scientists I read about did in the 1960s and 1970s, where they were playing around with lipids and finding how they could spontaneously do things like form bubbles. And one of these scientists is named David Deamer. Mm-hmm. So Deamer, though, while he has these very practical applications that came of his research and the research of other lipid scientists, he wanted to study lipids to understand life itself, life at its basics, because there's one hallmark of life that kind of gets overlooked. It's not as sexy maybe as metabolism or intelligence, but it's like life has boundaries. You and I are not just clouds of molecules that just sort of disperse in the wind. We are kept in place. We are sacs. Our skin closes us in, and the same is true for a cell. A cell, it has a membrane that encloses the chemicals that it needs to carry out the reactions to sustain life. And now our cell membranes are incredibly complex and have lots of proteins that move things in and out of the membrane. And so David Deamer was wondering, well, when we're thinking about how life began, we don't want to just think about, the origin of genes, but we need to think about the origin of these compartments. We need to think about how was there a place to put stuff in. And so this led him over the course of decades on a really marvelous chase after an idea that life may have begun in ponds on the flanks of volcanoes, perhaps, where they would fill up with water and then they would dry out. And basically you would get these oily lipid layers forming and sandwiching the forerunners of our genes in between them. And they would sort of be forced to do interesting chemistry. And then rain would fall into these ponds, and these lipid sandwiches would break apart and spontaneously form into liposomes, some of which might contain, say, RNA. So, that vaccine that you get with the liposome, with the RNA inside, is in a way kind of an echo of what some people think is how life began. But where you draw the line between a pond where some weird chemistry is happening and a pond where life has started is a very difficult line to draw. And yet, when we want to understand the origin of life, again, we have to figure out, well, what do we mean by life?
Well, I have a question. Can you talk about how life might have developed prior to the appearance of LUCA, which likely is comparatively sophisticated, and tell us what LUCA is?
LUCA as an acronym means the last universal common ancestor. So, all humans descend from a common ancestor or a population of common ancestors several 100,000 years ago. Humans and chimpanzees descend from a common ancestor that lived maybe 7-8 million years ago. And you can work your way back. All vertebrates on land descend from a common ancestor. That was some lobe-finned fish lived maybe 380 million years ago, something like that. So if you're drawing the tree of life, and each branch is a living species, plus draw some extinct species, but if you draw it all the way down, you get to the common ancestor of all living things on Earth. For the sake of this discussion, we'll just agree that includes bacteria, archaea, animals, plants, fungi, other eukaryotes. So LUCA is that thing that was at the base of that tree, but that LUCA was probably was probably a fairly sophisticated microbe. In other words, it was, probably something akin to bacteria, certain kinds of bacteria today. In other words, something that lived as a single cell, contained DNA, used that DNA to make proteins with ribosomes, the factory in all cells. So that's pretty complicated. And something like that is not going to pop into existence from the raw materials on Earth before there was life. There aren't just ribosomes lying around. But there would have been lots of different kinds of organic molecules lying around. And it's possible that there were some places on Earth that might have acted like chemical reactors. So David Deamer has been championing this idea that ponds, pools on the sides of these new volcanic islands 4 billion years ago could have been the reactor that produced life. Whereas other scientists have championed these chimneys that form at the bottom of the ocean, where incredibly hot water laced with minerals comes gushing out of the earth, and all sorts of crazy chemistry is happening all around them. Clearly, they both can't be right in the sense that, if life has one beginning, it can't happen in both places at once. Who knows? Maybe it happened in both places and one formed one and the other one went extinct. That would be pretty wild too. But that all happened long before LUCA. So LUCA, probably existed, say, 3.5 billion years ago, roughly speaking. So the first common ancestor, cellular life would have been maybe hundreds of millions of years before that.
So this morning, when I turned on my cell phone, it said, "Would you like to listen to What is Life by George Harrison?" What a nice coincidence. Good song.
Yeah, I got to listen to that again sometime.
Yeah. So someone says, "I love your books. Thank you so much. I was hoping you could talk a bit about your research and writing process."
The research and writing process. Yeah. As I was mentioning before, for books, I really do try to think about what has been sort of bubbling in my mind, because it's probably something that I would really enjoy exploring for a year or two, because I want to be spending time with a subject that I'm going to really enjoy being with. You don't want to get tired of something after a month. So there's usually like a while where I'm sort of turning ideas over, doing a little research, talking with people, trying to get a sense of what might work as a book. Once I get that, then I start to map the book out. I start doing research, maybe reading some of the history behind the subject I want to write about, and then start to think about, well, what kind of reporting can I do? So so I mentioned, these hallmarks of life that I was interested in. So I just thought, well, let me write about these exemplary lives. So I had known Simon Garnier. We had met before, and I'd always been fascinated with his slime mold work. And I said, I need to come spend a little time in your lab. And so I just hung out and just watched them work, and they would, show off experiments where, they would create a puzzle for the slime mold to solve, and then put a camera over it that would take a picture like I think every 5 or 10 minutes, and then just walk away. And we'd come back the next day, and the slime mold would have done something crazy that we could see on the petri dish that it had moved, and then we could watch a movie of those pictures. For metabolism, I hung out with a snake biologist in Alabama. We were feeding rats to snakes and just learning about how snakes just go through these incredible metabolic contortions to break down these things that they eat whole. They can eat practically their whole weight at once, and then they have to break it down over the course of days. And actually, that itself is the kind of metabolism that you see in racehorses. And these snakes are doing it for days, just lying there. The maybe the riskiest thing I did was when I was doing reporting on homeostasis, that inner balance that living things have. And I decided that, bats were my favorite example of that, because bats are keeping themselves balanced in all sorts of ways. They're balanced when they're in flight, and they can manage that balance even when there are gusts of wind blowing them in different directions. They keep their body temperature and their blood sugar steady all through the summer as they're catching food and racing around. And then in northern areas, they go and they hibernate, which means that they basically like completely shift their metabolism to a new state, and it's a new balance. And they can maintain that balance without eating anything and barely drinking anything for the whole winter. So to study them, you got to go where they are. And I went with some New York biologists who study bats in places like in the Adirondacks. So found myself in this abandoned graphite mine, which was great for the bats, but I don't think it's really good for humans. It's been basically falling apart for 100 years. So and we were, climbing over ice to get into it because, it was the winter and they were hibernating. Yeah, it was a wild experience, but a beautiful one, because you find these bats that are kind of like, they sort of look like furry pears just hanging from the ceiling and the walls, just alive. This is life as well, but a life that's so different from our own. It's fascinating.
Well, I'm glad I didn't read in his pursuit of what life is. Carl Zimmer ended up
Yeah.
being bitten by
Yeah.
a bat and causing the coronavirus. Okay.
That would have been an ironic biography, definitely. Yeah, the pandemic did sort of, I like everybody trying to write a book these days. The pandemic definitely imposed itself on my work. I didn't get to go to a couple places I had hoped to, but I ended up writing about the coronavirus in the book as one of these paradoxes of life. Is the coronavirus alive?
So do you believe life can be simulated by computers so as to study biological processes without direct observation of living things? I just read today that computers can now, they think, argue among themselves. And I said, okay, talk among
Yeah,
yourselves.
yes, there's this study about debating computers. I haven't read it yet. I'm curious. I mean, certainly there's no question that computers are very good and getting better at simulating a lot of life. So you can put pieces of a cell into this sort of simulation space and just watch them play out. But it's very difficult to really capture life in its full complexity in a computer. I'm not diminishing artificial intelligence, but when I've been writing about the coronavirus, I have been talking to some scientists, Rami Amaro and other scientists at University of California, San Diego, I believe, and they've been trying to create an artificial coronavirus atom by atom in a computer. In other words, a coronavirus where every atom just follows basic physics and behaves the way a virus is supposed to behave. They're still working on that. They've gotten, they've been able to sort of create a shell with the spike protein sticking off of it. And they can get the spike proteins to work pretty well, the way spike proteins probably do in real life, but it's empty inside. They're still filling it with genes and stuff. So, if computers still can't capture a virus in full detail, then I think we need to look realistically at what computers can do in terms of simulating life. Now, there's a separate issue of whether computers can sort of be a home to living things. So can you create like computer programs that are basically digital organisms, or artificial life, as it were? And this has been going on for decades now. And there's a whole field that calls itself artificial life. I will say that the scientists who are trying to make, protocells from scratch, trying to understand the origin of life, thinking about life on other planets, they look askance at artificial life. The way that one scientist put it to me is, well, I asked this one scientist, her name's Kate Adamala, University of Minnesota, and I said, so what do you think about artificial life? I mean, they call it life. Do you think it's life? She's like, no. I was like, oh, okay. I mean, she was not being diplomatic or sugarcoating it, just no. I was like, well, why not? She said, well, I have something I call the Goo Rule. So that's Goorule. And I was like, the Goo Rule, what is that? And she explained that, well, by goo, she means, the chemistry inside of cells, what has traditionally been called protoplasm. That's mysterious gelatinous stuff that people used to think has that vital force. And she said, look, if it doesn't have goo in it, it's not life. So, computer code is perfectly interesting, but for her, it's not life. So there's another example of how scientists, are continuing to make these sort of homebrew definitions of life, and do not agree on it. I mean, I've definitely talked to artificial life people who consider these digital organisms alive in all the ways that we find interesting in real life. They evolve, they can forage, they can do all sorts of interesting things. And so for those scientists, yeah, they're alive.
Okay. About 20 years ago, a biophysicist friend explained the seemingly purposeful actions of non-living viruses as an expression of the tendency of all chemical systems to seek equilibrium. Do you have any thoughts on this explanation?
I don't really see how that makes sense. When I think of seeking equilibrium, I think of stirring food dye into water and just having it disperse. Those kinds of reactions. Viruses are not seeking equilibrium. They're seeking in the blind nature of evolution to make more viruses. And by making more viruses, that's not going into equilibrium. That's just actually going further out of equilibrium. That's taking raw material and making more of these highly structured, information-rich entities that we call viruses. So, no, I don't buy that. I mean, I think viruses really are a deep puzzle because they don't have those ribosomes. They don't have metabolism. So they sort of seem like kind of these weird zombie robots that go into our cells and take them over. But they can evolve. They adapt. I mean, we're dealing with a revolution right now with these variants that that our vaccines may not work so well against. So it's much more than just this sort of just passive matter. Viruses pose a really deep and profound challenge to easy definitions of life.
Okay. Someone said, I'm very curious to know, what is the sticker on your microphone?
Oh, this was actually her name was Emma Townsend Seymour, who was a suffragette. And when I went and voted in the last election, the presidential election, they were handing out very cool "I voted" stickers, and this is a historical one from Ms. Seymour, who's a suffragette. So I just liked it so much, and I wanted to just stick it someplace. So boom, right there on my microphone.
So as I announced earlier, that today is the first 1-year anniversary of the World Health Organization describing this as a pandemic. And since then, you've been kind of reporting on COVID full time for the New York Times. So when doing this book, how were you able to balance those two?
Not easily. I think that, when
what stage was the book in a year ago?
I was in the process of trying to finish writing it, and then start to do fact checking and so on. So there was definitely a few months there where it was kind of crazy. But I mean, what did we think a year ago? I mean, I had a sense that this was going to be a pretty bad situation, but journalistically, I had no idea what I was getting into. I just said to my editor at the end of February, I see that you're starting to reorganize the science desk to really focus on COVID. And I've written for the Times about other viruses, about Ebola and influenza and so on. I've written about vaccines before. So I'm like, look, I have experience with this. I'm happy to join this team. And they're like, great, on board. And so that started ramping up and getting more and more intense. It's weird when you're, I mean, I think a lot of science writers are familiar with science writing as a relatively stately process, shall we say. Like, you spend time really getting into the science and working on a story, talking to a lot of people, thinking about it, rewriting your piece and so on. Maybe I'm biased because I started in magazines, but all of a sudden I was like, and people like Apurva Mandavili and other people on the science desk, we were just like working with the daily news teams and who were wanting us to file like an hour ago, like, and sometimes you were like filing 2 or 3 stories a day. I remember like I was filing on a vaccine trial result from it was a trial in Turkey that was for a Chinese vaccine, and I was filing a story about it Christmas morning, and I just thought, wow, this is a weird experience. So yeah, so basically I just tried. By the time things got really crazy with COVID, I was wrapping up the book. Thank goodness. yeah, I'll have to figure out how this all happened when things calm down again, whenever that is.
You've been my guest twice, and Apurva's also been my guest, so that's been kind of nice. So I have two more questions, and then you're gonna talk about where people can get the book.
Great.
You know, when we did it in person, I bought books, and you would autograph them and sell them to people. So that was a little different. Okay. Do we need to just let go of the concept of drawing bright lines between things, such as life and non-life? This is obviously a question of philosophy as much as science. So,
Yes.
I mean, I thought that, I mean, so my father died, 2015, and so one minute he's alive, and now he said, pronounced dead, and it's like, well, he's just a living being like 2 seconds ago, and now he's, and it's like, what's going on, So
Yeah.
I guess that's the question: is there a real demarcation?
There can be demarcations, but there can be situations where we're drawing a line that may not actually be there. When we talk about death, for example, philosophers tell us, we have to really be clear on what we mean when we talk about things. So the medical community, generally feels that brain death is death. But there have been conflicts and court battles over this because a person whose brain has no activity still has a lot of those hallmarks I was talking about before of life, of homeostasis, for example. So a person who is on a ventilator, they have steady body temperature, that they maintain themselves. They have, a steady level of nutrients like sugars and so on. Their bodies are maintaining that themselves. So if you choose that hallmark as defining life, then you might say, well, this person is still alive. But if you say, well, no, like life in the meaningful human sense is about the integration of living processes. Well, the most important integration happens in our brains, because that's where we sort of integrate all these things into our sense of self. So if that's gone, then our life in the meaningful sense is gone. So, you can't expect science just on its own to help you through those situations. Certainly science can tell you a lot of things about what's going on, but you have to think about, well, what is it that you're trying to ask about? And it's very difficult for us to say, like, oh, well, there's a gradation between life and non-life. Like, how could that be? I mean, you're alive or you're not. But there are things that do exist in this strange kind of shadow zone, not just viruses, lots of other things.
So I was having dinner with two of my college roommates, and one of them had heart surgery, and the other one was a heart surgeon. And he said, well, I had heart surgery. How do they operate on a heart? He said, because it's beating. He said, well, we stop it. He said, and he turned pale. He said, what do you mean you stop it? He said, I mean, I was dead. He said, no, your brain, we keep you alive. Your brain is still alive, but we stop your heart while you're doing it. And he was just like, I just like kicked my friends and said, I don't think he needs to know more than that. So here's the question. Were you surprised by anyone or anything that you encountered during the research and development of your wonderful book? If so, how were you changed by this experience?
I'm just trying. I mean, there were lots of surprises. I'm just trying to think of one. So I had a really interesting experience where, I mentioned I was, I profiled David Deemer in this book as a way of talking about the origin of life. And, I sort of think of like a question like the origin of life as science at its purest, like just, people study it just out of curiosity to understand the universe. And there's nothing, couldn't possibly be anything practical that came out of it. And in talking with David Deamer, I realized that that's not true. So David was imagining how do these protocells begin? Like what would the first cell look like? And he was like, well, like there would have to be a way for stuff to get in and out, but it'd have to be super simple. You'd have to have channels that could form spontaneously. You couldn't have fancy proteins creating tunnels and so on. And so he would fool around with lipid chemistry to figure out how that might work. And he was thinking like, well, like maybe you could pull in pieces of genetic molecules and use them to build genes inside. And he's thinking like, like, okay, I'm picturing a gene going through a pore. And he's like, like as that goes, it'll like set off a little change in the electric field inside the pore just because of the way that the atoms are arranged. He's like, wait a minute. If you were to do that, and if you could measure that electric field, you could read maybe the sequence of the nucleotides of the letters in that gene. In other words, this could be DNA sequencing, radically different from the way that other people were trying to do DNA sequencing. So he actually thought, oh, I better patent this. So he and some colleagues patented it and then worked on it for a number of years, and then a company acquired it. And decades later, this is something known as nanopore sequencing. This is you may see these nanopore sequencers. They're so cute. They're like this big, and you can plug them into a laptop. They're a really cheap, fast way to sequence DNA, and you can take them to places and do quick sampling. So like coronavirus samples are being sequenced with, in some cases, with nanopore sequencing. And now there are even plans to potentially put nanopore sequencers on space probes. So for example, there's a icy moon of Saturn called Enceladus, and there are these plumes of water, vapor that spray up out of its ocean, go through these cracks in the ice and go into space. So you could steer a space probe through that and just put stuff into your nanopore sequencer and see if there's anything even vaguely resembling DNA from living things under the ice. So that was a surprise.
Okay. So I want to get my plug-in for the interviews coming up. So next week I'm doing another book event with Sherry Turkle, whose book was rave reviews, and it's called The Empathy Diaries. Sherry's an MIT psychologist and best-selling author of Reclaiming Conversation Alone Together. That's March 18th. And March 24th, I'm going to speak to John Moore of Weill Cornell about the latest variants and how vaccines can cope with these variants and how well are they doing. On March 31st, we're going to talk about food scarcity in New York State during the COVID-19 pandemic with Avito Havusha, Vice President of Programs of New York State Health Foundation. On April 14th, we're going to speak with Helen Fisher for the second time a year later about dating and the pandemic 1 year later. So Carl, I want to thank you for your time. Here's the book. Where do people get it?
Well, you can get it fine bookstores that are actually open. Wear your mask, or order it online. You can find out more about it at my website, carlzimmer.com. And since I can't do book signings in person, if you want to let me know that you got the book, maybe put it on Twitter or something that you got it, that would be great. And contact me through my website, and I'll send you a signed book plate.
Okay. Well, thanks. So anyway, thanks for spending time with us. I know that President Biden is speaking today for the first time. And so I don't want to hold you up anymore. And we appreciate the time. We got a great turnout, and good luck with the book. And I'm sure it's going to do well.
Great. Well, thanks for having me. It's been real fun talking with you again.
Oh, it's been always fun. And so thank you for the presentation. P.L. Lucas Foundations in California. So it's nice to know Science Writers in New York is getting people from California. So thank you so much. We appreciate it. Thank you, Joe, for doing this. This is being recorded for YouTube, for our YouTube channel, and we'll send you the link tomorrow. And thanks again. Great seeing you, and stay safe. And I know you're going to get into the vaccine soon, so I'm sure you're looking forward to that.
Oh, yeah.
Okay, take care. Everyone, please stay safe and be careful out there. And it was wonderful talking to you again, Carl. Good.
All right.
Hope to see you in person.
Yeah.
Okay.
Let's talk again soon. Take care.
Bye-bye.